In this video, we're going to look at an example of local linearization. And basically what that means is we're going to find the equation of the line tangent to a function at a certain point. And we are going to say that the values of the outputs on the tangent line are going to be very close to the values of the outputs of the function near the point of tangency. All right, and that's basically what this is saying up here. But let's just jump in and get the equation of the tangent line, and then we'll look at the graph and get a better feel for what's happening here. So we want to find the equation of the line tangent to g of x at x equals 0. So we need to know our slope. And our slope is going to be the value of the derivative at that point. So we use our power rule to take our derivative, and we want our point of tangency to be at x equals 0. So that's going to give us a slope of 1. And our point of tangency, we'll plug in 0 into g, and we get 0. So pretty straightforward. We have a slope of 1 and a point of tangency of 0, 0. So the equation of our tangent line is y minus y equals slope times x minus x, and we get very nice y equals x. All right, so this is the equation of the tangent line. Let's go take a look at the graph. So here we have our g of x function, this cubic, and here we have our tangent line right here. At our point of tangency is 0, 0. And so with this local linearization, what we're really saying is that, let me turn off the tangent line here for a sec. If I zoom into this function right here, the more I zoom, it really starts to just look like a line. And that's kind of true for any place on the function. I can come all the way up here. You know, the more I zoom in, it looks like a line. So try that with any function. Local linearization. Zoom in to any point, even the curviest function you can think of, and as you zoom in, it really starts to look like a line. So if we find the equation of the tangent line near that point, then the outputs on the tangent line are going to give us very good estimates of the outputs on the function itself. So let's go back over here and just write a little notation. I would like to call this bit right here, this is the equation of the tangent line. Right, it's basically point slope form with this y value added over to the other side. I want to call this function L of x, L meaning like tangent line. So if we want to find the error meaning what's the difference in the actual value of the function and the approximation given to us by the tangent line. All right, so that's going to be f of x minus L of x. So this bit right here is all just this L of x up here with the subtraction right here distributed through. All right, so for our function down here, our L of x is x. So the error is going to be g of x minus L of x. So the actual value of the function at x would be given to us by x cubed plus x, and our approximation would just be x, and that comes out to be x cubed. All right, so what we're saying is g of x is very close to L of x for values of x near 0. All right, so g of 0.1, which is near 0, is really close to L of 0.1. Well, L of 0.1 is just 0.1, right? Because of our L of x is just x. All right, let me make this an approximation. But since it's an approximation, there is some error there. All right, so what's the error? Well, the error at 0.1 is 0.1 cubed. All right, so 1/10 cubed would be 1/1000th. So we know g of 0.1 is pretty close to 0.1. It's either 1/1000th more than that or 1/1000th less than that. Let's take a look at which direction it is. So this diagram kind of gives me a nice idea of what the error is. If I'm looking at some value of x and I do f of x minus L of x and the tangent line is below the curve, then the error is going to come out positive. So if the error comes out positive, your L of x is an underestimate. And that's going to be the case for our graph as well. I mean, I could zoom into point 1. It's going to be very difficult to see, but our tangent line is underneath our function. So the value of x at the tangent line is going to be a slight underestimate. So g of 0.1 is approximately 0.1. That's an underestimate of 1/1000th. The actual value of the function, of g of x is x cubed plus x, right? Which is, 0.101. There we go. All right, so this idea of local linearization is best if you're near your point of tangency. If we looked at x equals 0.2, let's see, the error at 0.2 would be 0.2 cubed, which is 0.008. All right, so we know the value of g at 0.2 is approximately 0.2 with an error of 0.008. All right, well, I hope this helps with local linearization.